Hello guys, welcome to BC Calculus. We are going to start lesson number 1, and lesson number 1 deals with limits. You probably got somewhat used to them, or in pre-calculus you were at least introduced to what limits are. I'm going to talk about them a little bit here, but this video or this lesson is broken up into 3 videos. The first one is about graph approach. The second one will be algebraically, and the third one will be the composition of limits. So if you were an AB last year, the first 2 parts you know pretty well, or at least hopefully you do. Part 3, you probably need a refresher on it, or it's brand new to you. So the first thing I want to talk about really quickly is what is a limit. And so you guys, the notation is absolutely really important here. So a limit as x approaches a. So we're basically looking at a function f of x, as you can see over here. And so as our graph is approaching some value of a, right, it doesn't matter if it's on the left side or the right side, but we're approaching a, we're going to get to this point where the graph hits at a, and then our limit is going to be the function, the value, the y value of the function where x is. So this is really going to be the point a, comma L. So when we're looking at the limit x approaches a, what is the corresponding y value? Now that's a very basic definition of a limit. It's not really truly a limit, but that's the idea of what you're going to be looking at. So if we look down here at example 1, we're given this function, right? We're given this function. And so we're asking you guys to find the limit of 4 different places. So x is approaching -5. So if we look over here at x approaches -5, well, this is a piecewise function, but right now we only really care about when x is going to -5. So if we come up here at -5 to our function, right, so we're looking at now this value, this point right here, we go over here to our corresponding y value, and we find that this limit is actually just equal to 4. Pretty easy, awesome, sweet. If we look at the limit as x approaches 2 of f of x, well, we're going to do the same thing. We're going to go up here from 2. Now, ladies and gentlemen, we'll talk about this a little bit later on. It does not matter right now that this is an open circle and the dot's up there. We're really just looking at the behavior of the graph, not and what's around that point, not what's happening exactly at that point. We'll get into this conversation a little bit later on. But if you're looking at this, we're looking at the value, and this is going to actually end up being 3. I'm going to go ahead and erase because I drew a lot of stuff right there for you to see that, again, if you're approaching x equals 2 from either the left-hand side or the right-hand side, our corresponding y value is going to be equal to 3. So pretty straightforward. You can probably do this next 2 ahead of me, so I encourage you guys to pause it and do them and come back to me here. We'll actually see it's a little bit different. So 0, if you're looking at so 0 is this value right here. Well, notice I don't hit, I hit it from the left right here, and I hit it from the right here. So there's no defining function at this value. We have a jump in our piecewise function, so this one is going to be does not exist. And you know, I always tell students, like, you don't have to do this, but I always like to mark out the equal sign because a limit does not exist. It doesn't equal does not exist. But yeah, so we're good with this one, I hope. And again, we're going to talk more about this, but there is a jump discontinuity right here, and so the limit will not exist. And then the last one is x approaches 4 of f of x. And so if you guys look at this, x equals 4, you'll see that it doesn't matter left or right hand side, we hit at 0, right? We hit at 0. So hopefully that makes sense. Straightforward, off the gate, we're good to go, right? So sometimes in examples 2 and 3, they'll give you a table. You can use your calculator to graph it. In number 3, you can use your table as we did in number 2 to see what we're doing with this problem. So use the table to estimate the limit as x approaches 0 of sine of x over x. Well, okay, so let's go ahead to question number 2. So question number 2, it's giving you guys a function, the limit as x approaches 0 of sine of x over x. So you will learn something really awesome pretty soon called L'Hopital's rule. And that's going to be how you're going to solve this problem without the use of a calculator. But right now we haven't learned what L'Hopital's rule says, so what you can do is use your calculator and you can graph the function, or you can simply look at the table. If you look at the table and you can see that 0 From the left-hand side, right, as we're going towards 0 on the negative side, you can see what the values of our function are. So 0.047, 0.454, 0.841. You can see that these numbers are getting closer and closer and closer to 1. And then on the right-hand side, if you guys look at what's happening to the right hand of 0, 3, 2, 1, you can see that they're actually a mirror image. This doesn't have to always be the same as these right here, but the pattern matters that we're approaching 1 this way, we're approaching 1 this way, so this overall limit is going to be equal to 1. All right, so that's actually pretty awesome for us. So a table can be useful for this, and then also literally look at for a graph. So we're looking at the sine of pi over x, right? Pi over x. And if you guys can see, based on what we talked about at the very beginning in part C right up here, we're going to look at this problem. It's going to be the limit. And so the left-hand side and the right-hand side are not matching, right? We have, again, a jump discontinuity. So our left-hand limit is going to be this value right here, and then our right-hand limit is going to be this value right here, and we're going to get to that right here with the one-sided limits. So this is going to not exist, all right, because there is, again, a jump discontinuity here. So let's go more into detail about question number 3 and 1C with left and right-hand limits. So what I want to do is highlight this particular part, and I'm just going to actually just use my little marker right here. So what does it mean by left and right hand limit? So we're going to do some examples of it now, but in order for the overall limit to exist, and this is what we've been finding, I don't know why it's taking me so long to circle all this. So in order for the overall limit to exist, and this is what we've found in examples 1 and 2 and 3, then the left hand limit and the right hand limit have to be equal to each other. All right, if that's the case, then whatever the values of these are will also be equal to the value of the limit. I want to say that really quickly, you guys can see that this is x to the a, and it's raised to a negative, and this is x to the a raised to the positive. So this is a left-hand limit, and this is our right-hand limit. Okay, so let's look at the next example down here at the bottom, and let's look and see if this will make sense to us. So for example number 4, we're looking at the left, right, and overall limit for -2. So -2. So what I tell students is that we have a little gathering here, right? Gathering on this street, right? So this is the street of -2. And so we want the west side people and the east side people to come to this street. So the west side people are coming on this road. This is our windy, windy road. It doesn't matter what's happening directly, like on the far side of this line. We just care about what's happening right here. What's happening when we get to -2. So I tell students that we've entered this street at mile marker 1, right? This is our y value. So this limit is going to be 1. And now we're going to care about the east side people. Well, the east side people are coming this way, and then they hit the street of x equals -2 at the mile marker 0, right? So if these two limits do not exist, so I'm going to go ahead and write that down right now. If the limit from the left of our function, and pay attention to notation, right? You got to make sure that you guys are really good at that, and we'll do that a lot in this course. If these limits equal each other, all right, which clearly they do not here, but if they equal each other, then that we can say that the limit, as the overall limit, will exist, okay? And each of these numbers, this would be, if this is 5, this is 5, this is 5, it's going to exist. On the other side of it, the example we just did here, if the left-hand limit does not equal the right-hand limit, and they can have values, as you guys have seen in A and B here, then I automatically know that the overall limit will not exist. Okay, it does not exist. So I don't even have to do any thinking here. I know this answer is going to be does not exist. Just because these two numbers are not equal. If these numbers are equal, there's your answer. If these numbers are not equal, it always does not exist. It's as simple and as basic as that. Okay, so again, I encourage you guys to go ahead and pause this example and see, you know, if you can do D through I pretty quickly, and I'm sure you can, and we're going to come back and do them together. Okay. All right, so let's look at D, E, and F. So now our popular street that we're going to is x is equal to 2, right? And so This is a little bit easier to see. So now we're looking at the right-hand side, right? So this is plus. So the right-hand side. So we're looking on the right of this. And so we're going on our street and we're hitting this line at x equals 3, or sorry, y equals 3. And then left-hand side, we're going on the street and we hit this at 0. And just like before, our left-hand limit does not equal our right-hand limit, so I'll automatically know that this does not exist. Pretty sweet, pretty awesome, basic stuff. All right, and then the last one is what's going on with 0, right? What's going on with 0? So 0 from the left, so here's our little fun street one more time. 0 from the left, we hit it at 1. 0 from the right, we also hit it at 1. Since these two numbers are equal to each other, this is also 1. I don't want you guys, and I'm going to erase this for a second so you can see it. I don't want you guys to get burdened down by students like, well, there's a hole right here. That doesn't matter for limits. Okay. Again, we'll get into that in a future lesson about what this actually means with continuity. But the limit exists because both the left and right hand people meet on the street at the same value of 1. So it doesn't matter if this is filled in or if this is open, the limit will still exist. And when I talk about discontinuities with you guys in lesson number 2, I want to say 2 or 3, I will explain that a little bit more to you. Okay, so that's basic limits graphically with left and right hand side. I just want to stress before we move on to the next example is that notation is key. Notation is key. You have to do it. If you drop the limit part, then the function can be anything, right? And I'll talk more about that throughout this course. But you want to make sure that one thing you guys got to get used to right off the bat is notation is important. Over here, I'll be honest with you guys, this word does not exist. You probably saw that. And then I'll say, oh no, I got to write the function first. So you want to make sure that you actually write the function for it. You also want to talk about where we're approaching our value for C. All right. So let's move on to the next examples. So example number 5 is a question where you're not given a graph. So one of the things my expectations for you guys to do is look at parent functions. Look at what parent functions are. So this is a little bit more crazy than other ones because the parent function that you should be familiar with is the absolute value of x over x, which I know I didn't write it like that. I wrote x over the absolute value of x because that mimics this. Because it doesn't matter where the absolute value of this is, it's going to give you the same function, right? It's going to give you the same function. So this is equal to the same thing. So in this particular example, what we want to do here is this. We want to manipulate this, right? Manipulate this to where we know what this is. Because we know what this graph looks like. We know that this graph looks like this. Or at least we should know that this graph looks like this. And if you're not sure, ladies and gentlemen, you can always plug in values. You can always plug in 1 and say it's 1 over 1, which is 1. 2 over 2 is 1. 5 over 5 is 5. It's 1. Negative 1 over negative 1. Well, this becomes positive 1, right? So it's negative 1 over 1, which would be negative 1, and et cetera, et cetera, et cetera. So we first of all can see that we have a minus 3 here. So we know that our limit, we know we're looking at now the graph for x minus 3 over x minus 3. So what does that do? That just shifts, right? That just shifts our graph now not at 0, but now at x equals 3, right? So now our graph looks like that, x equals 3. So what we want to do is now look at this and compare it to what we have here. The first thing I want to acknowledge to you guys is notation is key here. You want to write down the limit as x approaches 3. Now we want to look at it from the left, right? This is our left-hand limit, the left, and we want to get this equation into this form right here. Well, we have a 3 minus x in the top. We want an x minus 3. Well, that's very easy to do. All we have to do is undistribute a negative 1, right? So then if I would distribute the negative back in here, I get negative x plus 3, and then we get back to this right here. So what does that do to this graph right here? So this is the same thing as this. Now, what do we do to compare these two? Well, if it's negative, it simply flips them over. So let me actually erase all this craziness here and draw it better than that. Draw it a little bit better for you so you guys can now see kind of what's going on. And most of you, you're able to do this, pretty straightforward anyways. So at x equals 3, now our graph's going to look this way and this way. And so this is at -1, and this value right here is actually at +1. So if we're looking at 3 from the left, all right, so this goes back to we had the conversation in the previous page. Here's our straight, here's our fun thing here, 3. We're looking at it from the left, right? We're coming in it on the left-hand side. Well, that's at y = 1. So this limit is going to be equal to +1, right? +1 and not -1. So just this question is testing, do students know parent functions? Do they know the transformations of the parent functions? And then can they manipulate this function that was given to you into something that you know how to graph pretty easily? Okay, pretty easily to do. All right. There is another strategy that I will give you in the part 2 of this lesson on this example. So let's say this had been 5 minus x over the absolute value of x minus 3. Then I'm going to give you guys a strategy on this. And the funny thing is, I think it's example number 5 in part 2. So take a look at that and then come back and see if you want to solve it a little bit differently. All right. For question number 6, we're looking at the limit as x approaches 2 of f of x, and we're given a piecewise function. Now, guys, I just want to say something very, very straight off the point with this, is that if we're looking at a function and we're looking at the overall limit, we're looking at a piecewise function. We don't need to graph this, but if we were to look at where x is equal to 2, right, as x equals 2, to the left-hand side, we would have the line y equals 3x plus 1. At x equals 2, we would have the point 2, 8. So this is basically saying that the function's defined at 2, 8. And then to the right of x equals 2, we would have the parabola x squared plus 3. We don't need to graph that. All I need for you guys to take out of this is that if I'm looking at this line, right, here's our fun line again. If I'm looking at x is less than 2, that's something over here, right? That's over here. That's the left-hand limit. So the less than is for left-hand limit, okay? So what does that mean in calculus? So if I want to find the overall limit and I'm not given that, I have to take the left-hand side first, and I have to do something that we just do substitution, very basic substitution. Please do not think that the limit is equal to this. This is where it's defined. And this is very similar, if we can go back for a second, to our very first example. And let me again erase some stuff here. Go back to this very first example and see that our function at 2 is defined at 5, right? Our function is defined at 2, 5, but the overall limit we decided was 3 because it's what the behavior of the graph is at that value, not what the actual function is defined. So just let's make sure that we kind of remember that when we're doing these problems. So this is actually not even important to us right now when we're trying to find the limit. It's important to us when we're talking about continuity, which we'll get to in another lesson, but right now we don't care about that. So we're going to plug in 2. It doesn't matter it's 2 to the left. We're just plugging in 2 here because if the left-hand limit exists and the right-hand limit exists, then the overall limit is going to be the same value. So we just plug in 2 right here, and we're going to get 7. So I know that when I look at this function, to the left of 2, my function is going to be at 7. Then I look at 2 from the right of our function. Well, this is going to be our right-hand limit, right? Our right-hand limit, and this is going to be where it's greater than. So guys, what I want you to take out of this is if you look at a piecewise function, anything that's to the left is going to be less than, anything to the right is going to be greater than. So we're going to go ahead and write down x squared plus 3. We're going to do substitution in here. We're going to do 2 squared root is 4. 4 plus 3 is 7. So again, notice my notation. It's really important that we do this. And so since I know my left-hand limit is equal to 7 and my right-hand limit is equal to 7, I can now say that the overall limit, well, actually, let me say first before I do that, that because the left-hand limit is equal to the right-hand limit, again, don't forget your functions, I can then say that the overall limit, so I can infer that the overall limit is going to be equal to, it will exist, and it will also be equal to the values of this right here. And that goes back to what we did here, is that if the left-hand limit and the right-hand limit are equal to the same values, then the overall limit is also equal to that. If these numbers had been different, as you guys have seen in these 2 examples right here, if this had not been 7 and 7, then this limit just would not exist. Okay, so that's basically question number 6. So again, I'm hoping this makes sense to you guys, and let's move on to our last couple of examples. Okay, so let's look at example 7a. It basically says that sometimes, always, and never. I'm not a fan of these guys. I don't like these, and I don't like true false. I always feel like when I was a student, I always really overthought them. The only reason they're in the notes is just to give you guys a perspective of kind of just thinking. I'm not a big fan of testing you guys on sometimes, always, nevers, and true falses just because it's just not my thing. Will they sometimes be on assessments? Possibly, but very, very rarely will they be because I just am not a big fan of them because, like I said, I always overthink them when I was in school. But this is kind of cool because it's saying, okay, if the overall limit does not exist, what can I say about the right hand limit? Well, I know based on what we've actually already talked about in this video that if my right hand limit exists, so let's go ahead and call this a. And so I've got a function. And so if I look at the right hand limit of this function, that limit's going to exist at whatever this value is here. We call this b. And let's say that I have the same function doing something like this. So my left hand limit is going to be whatever this value is, c here, right? So this is a piecewise function where my right hand limit is this, my left hand limit is this, but my overall limit's not this. If that's confusing you, then let me go back to an example that's easier for you to see, and we're looking right here at this. So you can see that the right hand limit does exist, the left hand limit exists, but the overall limit does not exist. So in this particular example, this is going to be sometimes, right? This is going to be sometimes. Because the right hand limit also does not have to exist, and we will get to that in the next example. So it can exist, it doesn't have to exist, but this is sometimes. And this is your good old counterexample of when it does happen. And when it doesn't happen is when we talk about infinity, and we're going to get to that in a little bit of time. Actually, will be our example number 8. For part B, I will tell you guys right now, it's a little bit tricky. I'm not going to, again, like I said, this is why I'm not a big fan of this. It says that if the limit as x approaches 2 from the right does not exist, so my right hand limit doesn't exist, can I say that my overall limit does not exist? Now, I will tell you in an AB class, and even for you guys in BC, I would tell you that this should be always. That if the right hand limit doesn't exist, then the overall limit will not exist. So I'm going to say this is going to be always for you. But there's people in the math community that says that this could be a sometimes. Because if this right hand limit doesn't exist, we can look at this function right here, where if you're looking at endpoint limits, sometimes we have a discussion through the calculus community about endpoint limits. Do they exist? Will the overall limit of this exist? And this obviously would be at 2, right? This would be at 2. So this function, this is the xy axis. So something like this, where our left-hand limit would exist, but we don't have anything over here. There could be an asymptote at x equals 2, right? So could the right-hand limit not exist, but the overall limit exists? I know this is really confusing, so I'm just going to tell you right now that this, for our purposes, we're going to say always. So what I want you guys to get out of this is if the left-hand limit doesn't exist, nor does the right-hand limit exist, then just assume in this class that the overall limit will not exist. Okay, so we're going to say always. We're not going to get into a conversation about the endpoint limits. Okay, 2 more examples. We're going to talk about infinite limits now. So let me get rid of all this little crazy right here. So infinite limits. So sometimes the limit may not exist just because it goes to infinity. And so you guys have had practice with this, I want to say in pre-calculus if you got to it. And the notation for this just basically says that if we have a limit that's going to infinity, or negative infinity, plus or minus infinity, then really what's happening is my function is just exponentially going like up like this. There could just be like y, this is y equals e to the x, right? It's just going to go up, or there could be an asymptote somewhere and it's going to approach it from infinity. It's going to always be going towards infinity, but never quite getting there. And it could be restricted by an asymptote, or it can be restricted by nothing. And the same thing can happen with the negative infinity. All right, so really what we're looking at for here is when you're looking at graphs, particularly, you're going to be looking for asymptotes. So for example 8a, we're looking at -2 to the right, -2 from the left, and then -2. So if we're looking at -2, right, -2 from the left, from the right, right, looking at this -2, here's our fun street. Again, we're looking at from the right, well, this is going to be positive infinity. Now, students are asking me every year, does that also mean does not exist? Is positive infinity? Yes, you can also write does not exist here, and that's totally fine. what they're going to get you guys to do, usually multiple choice, is positive infinity would be the answer that you would choose. You're never going to be choosing between both of them. So positive infinity is correct here, so is does not exist. The limit as x approaches 2 from the left is also positive infinity, or does not exist. I will tell you guys, and we'll get to this conversation in our last example of this video, is yes, you don't want to say that this is equal to positive infinity because these two numbers are not the same. They're not the same thing. So if you have at least one infinity, I don't care if it's positive or negative, this limit will always be does not exist. Okay, always not exist. Not positive infinity. You don't want to write positive infinity for the overall limit. It will just not straightforward exist. If we look at example number D, E, and F, we're looking at now 3, right? We're looking at 3. Well, 3 from the left is going towards positive infinity, right? We're going over here, so this is going to be positive infinity. 3 from the right is going to be this value of 0, right? I know that people are like, we shouldn't be crossing the horizontal or the vertical asymptote. It's totally fine. It's just a point here. I would have it open, to be honest with you, if I were drawing this picture, but it doesn't matter. Again, it's what's the behavior of the graph, not specifically what's going on with the point. And then x equals 3, because these do not equal to each other, then clearly it does not exist. And then the last one we're going to look at here is 0 from the right. So here's our fun little street. 0 from the right is going to be positive infinity. 0 from the left is going to be negative infinity. And again, because of the fact that there's at least one infinity here, the answer is does not exist. All right. And then our last example of this lesson is, what if we can do, again, not a big fan of true false, but I do like this for a reason. So the limit as x approaches a of f of x is equal to infinity. And the limit as x approaches a of g of x is also equal to infinity. Can we make the assumption that infinity minus infinity, and we're going to talk about compositions. We're going to do this actually in the third part of this lesson, in the third video. So it's really just going to be the limit as of a minus this. Can we assume that infinity minus infinity is equal to 0? Is this a true statement? And the answer is no. This is a false statement. And I just want to tell you guys two things about this. That infinity is an idea. It's not a defined value. So this infinity may be represented differently than this one. And the example that I like to show you, like I tell students in class, is that we have 2 billionaires, right? We have 2 billionaires or trillionaires. I don't care. We have 2 billionaires. And I ask you guys to subtract the difference of their money. And we can't assume that billionaire A has the exact same amount of money as billionaire B does. So we cannot assume that this is going to be 0. All right. And like I said, this right here, this little part, we're going to get into this a little bit more. Where it's not infinity, it's like actual values. We'll get into this in the third video of this lesson. And then we get into why infinity minus infinity does not equal 0. We do more with L'Hopital later in the course. All right, so there we go. I'm going to end the video here for this one. I hope that this made sense to you guys. Come back. We'll do video number 2 with computing limits algebraically. And then, like I said, we'll do video number 3, which is going to be composition of limits. So I'll talk to you guys in the next video.